So we keep these stocks 1 month ahead in this period here, of t0 to t minus 1. And next month we update it, yeah? So next month t0 is obviously here. That's now our new t0. And we move this time window here 1 month ahead. So again, given the new t0, we again cumulate the returns from t minus 12 until our new t minus 1, yeah? And we do the same thing again. Okay? We check the stocks, we compound the cumulative returns for all stocks on our stock universe. Yeah? We buy those 10% of stocks that have the highest cumulative return, and we finance this position by shorting all stocks that have the lowest cumulative return in that period here. Yeah? Again, winners minus losers. So we update it every month. So obviously deciding are the cumulative returns, yeah, within this time window here. And okay, why do we skip 1 month? There's obviously a 1 month lag here, and okay, the reason is because of the short-term reversal effect. Okay, so but that's not so important to discuss right now. The important thing is, okay, we have here a accumulation period where we compound the cumulative returns, and the cumulative return should have predictive power for the holding period return, or for the predicted return. So that is basically the issue. And there are many different momentum strategies, obviously. So we can accumulate in this period. We can also, some strategies accumulate from in a 6 months time window here, or a 3 months time window, or they keep it not 1 month or 6 months. So there are many different, obviously, combinations possible. Yeah? But obviously, what momentum suggests is that the higher the cumulative return in this period here, yeah, or whatever it may be, has a predictive power for the holding period return. So there's a positive, it's this positive autocorrelation. Okay? Higher cumulative returns, higher predictive returns. Yeah? This is basically what momentum suggests. Let's take this away. Because now we want to talk about Fermat death regressions. And we take momentum now as an example of how it works. So let's say we are in t is equal to 1. And we know we have t 1 to capital T observations. We have capital T observations. And let's say, okay, we have n, capital N is the number of stocks that we consider. Let's define a vector. And again, we are now in t is equal to 1, in t1. Let's define a vector y, and let's put in here the excess returns, the excess return of the first stock. And again, now we add t is equal to 1. The second element here are the excess returns of the second stock given time t is equal to 1. And here the last element, of course, are the excess returns of stock number n, yeah, given time t is 1. So our y is obviously a n by 1 vector, so the dimension is n by 1. Yeah? Let's also define X matrix, and the first column vector in our X matrix is simply a vector of 1s. Yeah? The second column vector of our X matrix are the cumulative returns. Yeah? The first element here are the cumulative returns. CR is now our abbreviation here. Cumulative returns of that stock here, of the first stock in our y vector, given the period t minus 2 and t minus 12. Okay? The second element here are the cumulative returns for the second stock given between time t minus 2 and again t minus 12. Yeah? Because we just spoke about that we cumulate the returns in this time window here. And so on. Yeah? The last element obviously are the cumulative returns of the last stock here given between time t minus 2 and t minus 12. So the dimension of our X matrix is obviously n by 2. Next, we compound a matrix W. Yeah. And how does this matrix look like? So, we have on the main diagonal, the first element here on the main diagonal, element 1, 1, is the market capitalization, MC, the market cap of the first stock given time t minus 1 at t minus 1 divided by the total market cap. Okay? Divided by the total market cap. So let's say we have a market cap of 1000 and the first stock has a market cap of 2. So the element that would be here would be 2 over 1000. Okay? The element here in row 1, column 2 is 0. So we have only elements on the main diagonal. And on the main diagonal what we have is the corresponding market capitalization divided by the total market capitalization for each single stock given time t equal to 1. Yeah? So only on the main diagonal elements, the last element, element n, so row n, column n, we have the market cap of stock number n, our last stock, given time t is equal to 1, divided by the total. And everywhere else are zeros. Just write a big 0 here. Okay? So the matrix has a dimension n by n. That was the n by n matrix. And it's a weighting matrix. That's why obviously I denoted this matrix as W. Yeah? It's a weighting matrix. Where we have only elements on the main diagonal. So and again, we do this for, this is how we would define these vectors or matrices for time t is equal to 1. At time t is equal to 2, we would obviously have a new vector here, and a new vector here, a new matrix here, and a new matrix here. Because obviously the market cap changes over time. And the cumulative returns change over time. And the exact returns for each stock obviously change over time as well. So having these defined as matrices, we can estimate our beta hat. Yeah? So we know from econometrics class, beta hat given time t, and now t is equal to 1 obviously. And I write here also a W because it's weighted, it's basically, we use this weighting matrix, so it's a weighted estimator. Is then, how would you compound it? Okay, it's x prime, x transposed, times the weighting matrix, times x, inverted, to the power of minus 1, times x transposed, here, x transposed, times again the weighting matrix, times y. Yeah. So what we see is, this guy here transposed becomes a becomes 2 by 1 matrix times 2 by n matrix, sorry, times n by n times n by 2. So what is here is a 2 by 2 matrix inverted. This transpose is 2 by n, so 2 by 2, what is here in parentheses is 2 by 2 times 2 by n times n by n times n by y. So what comes out here is obviously a 2 by 1 vector. Yeah? Our beta hat 1 and our beta hat 2. So it's a 2 by 1 vector. So if we now go to the next iteration, if we take the data for t equal to 2, so what we would get here is a new vector which has also the dimension 2 by n. Yeah? So we always get an estimator here, yeah, which corresponds to our, which is basically related to our cumulative returns, because again we want to investigate if the cumulative returns have predictive power for our exact returns. Yeah? So this guy here obviously gives us how much the exact return given time t1 changes if our cumulative returns increase by 1 unit. Okay? This is basically what this beta hat tells us. Yeah? We are not interested in this case, or at this stage, we are not interested at beta hat 1. Yeah? But we need it, of course, in order to run our estimation procedure. Okay? But our important estimator is what is here, this beta hat 2. So for each iteration, 1 to capital T, we can repeat the same regression. It's cross-sectional regression, because we have here the cross-sectional vectors for each point in time. We use always a cross-sectional vector, which has a dimension n by 1. Okay? So we do this capital T times, and we get capital T estimates for our beta hat 2. So we take this away now. Hopefully you made your notes. So we store in each iteration this guy here in a matrix, or in a vector basically. So for the first iteration, t is equal to 1, given t equal to 1, we get the point estimate, then we get a point estimate for beta hat 2 for t is equal to 2, and so on and so forth, and we get a point estimate for beta 2 given t is equal to capital T. So basically what we have here is a 1 by t vector, right? It's a 1 by t vector. So we can now take away this also. And of course, what we can do is we can transpose this vector. If we transpose this vector, what we get is a column vector that has the dimension t by 1 then, okay? So that's a very simple application. So what we do next is we compound a new, after we have done that and we have stored our results in this vector, what we do next is we construct a new vector, let's call it capital Y lambda, and let's just take this away, this beta vector. We have it in mind. We can write it also, let's write it here as a column vector. Yeah. So beta 1, beta 2 for time t is 1. Beta 2 for time t is 2. And here beta hat 2 capital T. Okay? Now it's a t by 1 vector. So let's take away this guy here. We have written it up there. We remember that. And we can move this a little bit higher. So let's construct a new vector and call it y, capital Y, lambda. So what's in this vector? So the first element is the expectation over I of the excess returns from stock I, from I1 to capital N, given time t is 1. Second element, we take the expectation over I, again, our excess returns from stock I is 1 to capital N, given time t is 2. Okay? And the last element here is the expectation over I of our excess returns I, and I is 1 to capital N, given time t is capital T.